Hello everyone. In this video we're going to be talking about minimum spanning trees, which is one of the principal algorithms we talk about in this class, as well as a very good introduction to greedy algorithms, which are a certain class of algorithms that can be useful as long as you are careful about how you use them. So, let's begin talking about what a minimum spanning tree is. A minimum spanning tree is a spanning tree in the graph that has the least weight in some sense. So let's first draw some sort of spanning tree here. I'm going to draw a spanning tree that connects some of these edges, all of the vertices using some of the edges. So if we look at this, I've connected all of the vertices in orange here. We are going to talk about the weight of a spanning tree. So I'm going to call this a spanning tree T. The weight of T is the sum of the weights of all the edges. So this one would be 7 plus 2 plus 9 plus 3 plus 5 plus 5 plus 7. So this gives us 18, 21, 26, 31, 38 for a weight. The question is, can we do better than this spanning tree in terms of this weight? We want to find the tree that minimizes the weight. So, let's see if we can. It seems like we might have made some bad choices along the way. This edge with a weight of 9 doesn't seem like it might have been the best choice. So let's try a different one. I'm going to do this one in blue. So let's check this spanning tree. We go from here up. We go down here. What if we go along this edge there, then that edge there, then maybe we go up here, then maybe we go back that way, then maybe we go down that way. So that one now done in blue, or it appears green when it overlaps with the orange. Let's see what the weight of that one is. So we'll call this one T prime. The weight of T prime is 7 plus 2 plus 7 plus 1 plus 3 plus 5 plus 4. So let's check it. This is equal to, we have 9 plus 7 gives us 16, 17, 29. And again, we ask, is that the minimum? And that might be a hard question to answer. It actually turns out that in this graph, there is a minimum spanning tree that does a little bit better than this. So I'm going to emphasize this one by thickening the lines in a nice thick black pen, just to make it differentiated from the other two. So if we actually use this minimum spanning tree, V1 to V2, V2 to V6, V2 to V6, V2 to V3, we then take this edge as well, that edge as well, that edge, and that edge. So let's call that maybe A. This will be the weight of A. So let's compute the weight. 7 plus 2 plus 6 plus 5 plus 3 plus 4 plus 1. So that gives us 9 plus 6 is 15, 20, 23, 27, 28. It actually is better. And how do we know that's the minimum? Well, that's going to be a question we'll answer by proving some various theorems about these minimum spanning tree algorithms we're going to develop. So we will see that later. But for now, this is one way, this is what a minimum spanning tree is. We are going to see how could you possibly find this in a reasonable way. We'll see two different methods for doing that. We'll really focus on one first, and then the other one we'll mention as an alternative algorithm for some of these problems.